In this video, we will demonstrate how the Interactive Parallelization Tool, or IPT for short, can be used to parallelize an example that solves a circuit satisfiability problem. Below is a snippet from the main function of this program that shows a hotspot for parallelization. This section of code searches for the number of solutions by calling the function circuitValue for each input. The evaluation of each input with the circuit is performed in the function circuitValue, so the iterations of this for loop are independent and have no dependencies on one another. As a result, this loop is a good candidate for parallelization. However, one should notice that the variable solution num is being reduced in this loop. This will need to be called out explicitly to IPT later. We can invoke IPT from the command line and pass the source code as an argument by typing IPT and then the path to the file. IPT first prompts the user to select a parallel programming model. We will be using OpenMP for this example, so we will select option 2. The function that we wish to parallelize is in main, so we will select option 1. Next, IPT prompts us about which parallelization pattern we want to use. We will select for loop parallelization. Using the information we have provided, IPT performs analysis of the source code and presents potential for loops that can be parallelized. The first loop displayed is not our hotspot for parallelization, so we will tell IPT no. IPT will then look for the next loop and ask if this is the loop we want to parallelize. As we can see, it is in fact our targeted region, so we will tell IPT yes. Next, IPT will ask us if there are any reduction variables. As mentioned before, the variable solution num is being reduced, so we will say yes. IPT analyzes the code for possible reduction variables and displays them with their type. Solution num is option 4, so we will select it. Last, IPT will ask which reduction operation we want to use. If you remember from the code, solution num was updated by adding the previous value to the new value, which is option 1. For now, we will assume there are no additional steps involved in parallelizing this example. While IPT asks the user explicitly for certain types of data storage like reductions, IPT makes some inferences on its own by performing dependency analysis. However, if IPT is unsure about a variable or an array, it will ask the user for clarification. In this case, the array is updated in a single iteration, so we can select option 1. At this time, we do not need to do any scheduling. And there are no lines of code that we need to run in a single thread. Also, there are no other loops we need to parallelize. We will not do anything special for printing or add in any timing statements. Now we will compile and run this program. To compile the program with the Intel compiler, we will use the command icc with the flag q openmp and the file rows circuits openmp.c. As the code compiled without any errors, we can now run it. Before running OpenMP code, let's set the number of OpenMP threads using the following command. Now let's run and time the code using the command below. As you can see, the parallel version found 15 solutions, which is the same number of solutions found in the serial version. Let's increase the number of threads to 4 and see how that affects the runtime. Now let's try with 8 threads. And lastly, let's try with 16. By increasing the number of threads from 2 to 16, we were able to decrease the runtime by about a factor of 5 and still achieve the same results. Thank you so much for joining us today and watching. Have a great day.